Thanks for coming. Here are the plans for the future meetings. If you decide to so we are having two presentations today. Of course, you are time to see them on slide. So the first one will be by Aaron with strategic plan of the next iteration of research, next research project. And then there will be technical details, bringing the important finding that unties our hands and enables substantial progress for all of us. Among practicing computational chemists as of today, David will be potentially interested to literally repeat procedure that Brady will be describing. So in some sense, what you're doing is two-dimensional material as well.
Hi.
Oh! Honored to see you. You can take a honorable front seat.
Yeah.
You are serving as a good example of being humble, other things. So there will be two presentations, and if anyone has some ad hoc comments and wish to come up front and present something else, it's always possible. So now let me invite Aaron to the stage, and since we have about 2 hours for meeting, there are no limitations for this 12 slides.
Why long distance? Is somebody from LAN listening in? Or?
Eventually, I hope, yes. Today, probably not, but it is being recorded.
Okay.
So if we will be missing to see our own faces, or if there will be some important part of the discussion, we can get it back later.
Okay.
You don't have a secretary who sits and takes notes.
Thank goodness.
Any wise thought?
Yeah, so as Dmitry mentioned, this is kind of my broad outline in the beginning of calculations for my next set of calculations I'm going to be doing on my perovskite nanocrystal that many of you in the audience have seen before. And so I guess I'll jump to the first slide, which kind of pictorially represents what I've done so far. So these are just graphical abstracts for the last couple of papers we've put out. So on the left, we described the excited state carrier cooling and luminescence properties of a small perovskite nanocrystal atomistic model. So that's what this guy is here. So it's a 2 by 2 by 2 unit cell, passivated with ligands, which would reflect the kind of environment it would be in a colloidal system, approximately. And essentially what we measured is, based on the initial state, the hot carrier dynamics as it cools from non-equilibrium position to the band edge. And then from there modeled its luminescence properties and calculated a theoretical photoluminescence quantum yield by calculating radiative and non-radiative rates of relaxation from the band gap. And that gave a reasonable approximation to what people see in experiment. Usually in experiment they usually see a little bit higher yields, but it's not a one-to-one comparison because this model is a little smaller than what's seen in an experiment. But we have the right order of magnitude, so that was a sign that our methodology seems pretty robust to describe these systems. And then what we attempted to model after that is So for our first paper, we got by with an approximation where you can approximate the excited state dynamics by assuming ground state geometries, so without adding or removing electrons and holes from the system. But in reality, these perovskite systems, when you introduce charge into them, their geometries and structures will change a little bit due to polaron formation. Since they have a soft lattice, they'll react with, if you put an extra electron or extra hole in there, the geometry will reorganize and that'll change some of the excited state properties of these systems. So we explicitly accounted for adding either an electron or a hole into the system. And then that's what these pictures, so you put in a charge, either add an electron or remove an electron, do the same dynamics, essentially do the same calculations. And the provocative idea that we had for this model was modeling polaron photoluminescence. So if you had a hot polaron, that if you somehow could give it excess energy within the polaron potential well, that if you got a population inversion of your polaron, whether you can get photoluminescence from that. And we calculated that for a negative polaron and a positive polaron by himself, and we got fairly small yields computationally, and this is something that, from what I've seen, hasn't been looked at experimentally yet. For people who tried to look for photoluminescence signatures of polarons, well, they have seen absorption characteristics. So that was kind of the motivation of why to try to look at photoluminescence, because they are optically active in some sense.
And your left is visible and right is infrared.
Yes, so yeah, one way to characterize the radiative transitions, so this would be across the band gap, so interband radiative relaxation. While for polarons, you can describe it as intra radiative relaxation, so it's like so basically it would be a radiative relaxation from an excited band in the conduction band. Or that's how we attempted to model it anyway. And so yeah, this would give IR photoluminescence, while this would give visible luminescence. And so essentially the next idea that we want to do is to go a step further with modeling polarons in these systems. Is we want to consider development in the atomistic modeling and a development in the methodology to describe the excited state properties or the excited state dynamics in these systems. So for the modeling, we're going to include both negative and positive polarons simultaneously in the model, which would be reflective of an experiment. If you photo-excite it, it creates an electron in a hole. And then, so it would be modeling it like a realistic photo-excitation of these systems. And then, in terms of methodology, we're going to include electronic coherences of the species along the excited state trajectory, and that's kind of what we have planned next. So that's what this slide kind of visualizes. So both having a simultaneous positive and negative charge in the model, and including for the what we call the off-diagonal elements of the density matrix, which is describe coherences or resonances behind excited states. And typically we neglect them due to a timescale argument for how we typically do our modeling. But for polarons, it's expected that the lattices will kind of screen external phonons so that coherences should be extended in these models. So that's why we are picking to include coherences as the next methodological step. So, any questions so far?
Yes,
up to this point?
So the equation that you're showing doesn't have depopulation or dephasing, it's only coherent evolution. But you probably plan to include depopulation and decoherence.
Yes.
So for depopulation, it is dissipation of energy from electronic system to lattice vibrations.
Yeah, phonon.
Yes, phonons.
Yes.
And is there a similar interpretation, how to interpret the disappearance of diagonal elements of density matrix? Which physical mechanism is responsible for dephasing and decoherence?
I guess in solid state environments it would be phonons. Or
But how? More details. Because dephasing doesn't change energy of the system.
Mhm. So what's the mechanism behind dephasing?
I have a hypothetical answer, but maybe you have some different in mind. If it is an ensemble over several replicas, each of them interacts with phonons and may have offsetting energies, and in each of them the phase will be accumulating with different pace.
Mhm.
And upon average over ensemble, the phase accumulated with different phase will deconstructively interfere and remove of diagonal elements. So dephasing is a consequence of average over ensemble.
Is that represented by detuning?
Mm-hmm.
So it's essentially, could you say fluctuations as well?
Yes,
Is another way.
fluctuations is when we replace average over ensemble with average over time.
Okay.
But you don't object this interpretation.
I do not.
Okay.
And so, in terms of methodology, how to incorporate dephasing or phase relaxation into our excited state dynamics. So, I guess I'm going to start from the point of view itself. We generally compute non-adiabatic couplings. So that's what, like the resonances between electronic states or the energy that causes changes in populations. So these are two electronic states, I and J, and then superscript is just type of orbital. And it's just how phonons change electronic state along the trajectory, or couples two different electronic states, I and J. And to get transition rates between electronic states, you can take correlation functions of the couplings and then do a Fourier transform, which essentially gives you the phonon modes that they couple with. And then they give you rates of transitions between different electronic states. Yes.
If I'm allowed to.
Mm-hmm.
Very first slide. How would this V and A sub ij will look if you have I equals J? And what will be the interpretation?
How the wave function are the same state changes over time?
Okay. And
Or how much it breaks orthogonality
okay.
over time?
So this dimensionality of V is energy.
Yes.
So it's contribution to Hamiltonian if in some sense.
Mm-hmm.
And right now it is off diagonal parts. If I is not equal J,
Right.
would it be possible? Again, I'm not instructing. I'm checking. Hypothetical. Would it be possible for I equal J to replace this overall matrix element by just diagonal element of this Kohn-Sham Hamiltonian of the energy of orbital I as function of time? I can be wrong, I'm just asking.
So how the band fluctuates
Mm-hmm.
over time? Well, it seems like a direction you can go just starting from this expression.
Okay.
And then I guess I'll skip these and I'll come back to them later in the slides. But essentially, our methodology, so we develop rates and then they make up what we call a Redfield tensor. So that essentially describes the change in population and coherences of the density matrix for an electronic state coupled to some sort of a thermal bath. And so this Redfield tensor controls the dissipation rates of the density matrix, and usually in our equations we leave this exponential term out, and this disappears if you go through the full derivation. And then essentially, instead of dealing with this exponential term at every single time that you try to diagonalize or try to solve this equation, you can make an approximation that it's going to oscillate fairly quickly unless the energy terms up here are summed to zero.
Mm-hmm.
And that's what I describe here. So if you take these energy terms and just say if you only concern energy conservation or like resonances between all these states, those are going to be the most prominent. And so you have EI, J, K, L equals 0. And so if you just run through the indices, you have 3 different types of scenarios you can come across. So you can have when I is equal to J, and then K is equal to L. And that'll give you 0. So that gives you, in the notation I have, R, I, K, K. And that essentially represents a loss of population from I to state K. So electronic state I to electronic state K.
Does it look similar to Boltzmann equation practice?
I'm sure it's the same physics, and well, for years I have been asking in that way.
If you drop all non-linear terms, would it be absolutely equal or?
I'm not sure. Again, we need to sit down and straighten it all out. So,
Yeah, I'm pretty sure I need to sit down with the textbook and go through it because I think some of my indices got swept up, or they don't match what people usually use for convention for later in the slides. But so that's one scenario. So you got population transfer, and then you can also have another scenario where I is equal to K, and EJ is equal to EL, and then that's what I refer to as coherence relaxation. So it gives the transition rates between R, IJ. Yeah, IJ. And so that's essentially a loss of phase between 2 different electronic states. Or dephasing. And then you could also have the trivial solution, I guess. It's where all 3 of them equal to each other. Actually, no, I don't think that works, does it?
But
so equation.
technically it's okay. If all of them are equal, it's still you can get this resonance.
Oh no, yeah, that would work. Never mind.
But
Yeah,
it's
what-
a particular sub-case of population transfer.
Subpopulation.
Two boxes up, you have population transfer,
Mm-hmm.
and population relaxation is a base population transfer first, and then adds additional condition. So it's, in some sense, they're similar. So they do not affect off-diagonal elements; they affect only populations.
Okay.
First and third can be grouped together.
Okay. And so, knowing that we have these three scenarios, we can start from our Redfield tensor and just play some games with the indices to see. Yes.
I'm sorry, this already came up before, but you and somebody else in the audience, qualitatively, how do I think about this coherence relaxation? Loss of phase between state I and state J. So what? What? Okay. Professor Killen seems to be happy. Qualitatively, what is it? What is it? What is happening? Due to phonons, right? It came up just a few minutes ago. But what? Just trying to get qualitative picture here.
Mm-hmm. So, I guess if two states, if you call them in phase, they can, depending on the type of coupling that you have, they can cycle
Right.
between electronic states coherently. And then dephasing is the rate that relaxation between, or the oscillation between states, like I guess you would say dampens out. And so it essentially doesn't allow coherent driving between the two states.
Quite a mixture. So, I remember, when Griffiths, which I happen to have taught, it matters, the relative phase between two states matters, right, if you compute the probability. How the heck does
So
it
suppose you compute current correlation
Okay.
as function of time.
Okay.
Will it be constant or will it relax?
Who knows? I don't know. Depends.
In experiment, it will oscillate and relax quickly. And for time-independent things, one will integrate over time, but or whatever, take Fourier transform. So how quickly these oscillations stop will depend on this dephasing.
Okay. Okay. Yeah, just trying to get a picture here. So.
Mm-hmm. Yeah, I know I have some MATLAB software that has pictures that describes, or it has plots that describes dephasing between two states, but I didn't put them in this presentation, but I can do them next time. I
Yeah,
present.
good idea. If we keep in mind only single isolated quantum system, then it doesn't make sense at all. It will not be possible to interpret. So it is a consequence of the average over ensemble.
Okay.
So, yeah, starting from a Redfield tensor, if we do the same indice plots and then look at how the corresponding rates between electronic states look. So if we just look at population transfer for I equals J, K equals L, it gives R, I, K, K. And then in the expression above, essentially the terms of the Kronecker deltas go away. So we're just left with the upwards and downwards thermal excitations or de-excitations. And in practice, the thermal excitations, or the plus term, will be much, much less than the thermal excitations due to Boltzmann factors or a detailed balance. So essentially this minus term will be the prominent rates for the dynamics. And then so that's the population transfer. And then if you do coherence relaxation, do I equals K, K equals L. So we end up with the same upward and downward transitions between two different resonance states, but we also end up with states that we have to sum over. And I guess I'm not sure. I think this is where my choice of indices might have led me astray in some cases, because I think if I actually went through and pulled terms out, I end up double counting some transition rates. So yeah, this is the same Redfield equation I was describing previously. And then from these, I just went a step further to look at how or what couplings I'll need to compute to be able to calculate each of these rates. And these I'm not very confident in, so I'm not going to spend too much time laboring them.
Mm-hmm.
But at the end of the day, essentially what I have to do is compute a bunch of electronic couplings between a bunch of different states with initial conditions, and then take correlation functions between those couplings. So I'll have time to work out the fine details later while I'm doing my calculations.
Thank you. And it would be really interesting, at least for me personally, to prove right or wrong if one can replace this V II by just energy of orbital as function of time, and then plug it into this procedure, because then the circle will close and it will coincide with many other independent methods.
Mm-hmm.
I don't have proof, but it looks tempting.
Okay, so that's the last of going over methodology and pulling stuff like that. So onto modeling, or the types of systems I'm going to be doing optimizations and calculations for. So the place to start was looking on the left. So this is just a general cartoon or schematic for electronic bands for quantum dot systems. So this is the band gap. So this would be the conduction band edge, valence band edge, and then the next closest electronic states in the conduction and valence band. And essentially what I'm doing is I'm screening 8 different possible configurations that the polaron could take in the polaron ground state and in the polaron excited state. And so
Aaron, I apologize for interrupting. Before we go further, can you please remind all of us why do you employ this SEPE, SHPH notations?
So when people do calculations for spherical potentials, they find that there's I guess symmetry in their wave functions, and that produces conservations. And so these correspond to momentum states, and it's expected that when you try to describe transitions between states, that angular momentum should be conserved. And so it's just the shorthand notation to describe bands and then transitions between bands and what would be expected.
Okay. But in practical, narrow sense, it will be like HOMO -1, -2, -3,
Right.
and LUMO +1, +2, +3.
Yes, and like in the software anyway,
Mm-hmm.
I'm trying to look at the data.
And why the arrows are going up and down?
I forgot to take them out, but they describe potential transitions that we want to look at for the system. And so if you started with an occupation in this, what I call P band, you could have possible radiative transitions or non-radiative transitions to a lower state, or even other possible ones too, but this is the most likely one. And so these are just describing infrared possible transitions, the UV light emission, and then also some more IR emission possibilities.
Would it be correct to say that spaces between vertical dashed lines are electronic configurations, or for some rigorous audience maybe different determinants or electronic configuration of a system?
You mean these?
Like between, if you pairs of your arrows enclosed between
Oh, these?
yeah.
Yeah, so yeah, each one of these is like a different initial condition that I'm going to be modeling. So in VASP, you can explicitly tell it where to put charges, or in what bands to put charges. And so I'm explicitly telling the software to put a charge in the LUMO band, and then remove a charge from the HOMO band, and then just let the software go. And then in this case, these arrows, they represent spin degrees of freedom. That's what we're going to try to model. So you have two scenarios where they can be anti-aligned or aligned. So that's why I break these up into singlet and triplet. Because triplet have aligned spins, singlet have anti-aligned. So yeah, this is just a messy diagram showing the possible states or the models that I'm going to be computing couplings for once I get them optimized.
So for each multiplicity, you have 4 configurations.
Mm-hmm.
And would it be correct to say that configurations are aligned with increase of their total energy? That as far we go from left to right, the energy will be higher, or not quite?
I think if I took the second column,
Oh, this.
moved it to the end,
Okay.
because this should be more destabilizing, because you're removing a more bound charge and placing it into a higher unbonded state. So the energy should be, total energy should be higher. So yeah, that's something I plan to be more meticulous about this time around, is actually comparing total energies for all the systems and seeing if the trends make sense.
Can I ask a provocative question?
Mhm.
Which next slide is answering anyway. So, why are you calling these excitations polarons? Why are they not just electronic excitations?
Because there should be, the charges should couple to the lattice that they're in, and since perovskites are generally soft, there's a reorganization of the nuclei around the charges, and so that's kind of the definition of a polaron in words anyway. So that's why I call them polarons.
Mm-hmm.
And I guess the interesting thing for these models is that since they're so small, or essentially you're placing a positive and a negative charge in like a 2 by 2 by 2 nanometer box, it's whether, since they're overlapping, whether you have like cancellation of the charges or if they somehow try to optimize themselves in. Well, I guess they'd be attracting since they're opposite charges, but it could be that the negative charge, like the effect the negative charge has on a phonon, and then the positive charge has on a phonon, that they could cancel out potentially.
It is an interesting, both numerical and experimental experiments. If you like continue whatever you're doing right now, compute infrared spectra of coexisting polarons, and then compare them with what you did before for standalone positive and negative polarons.
Mm-hmm.
If the coexisting will be equal to sum of positive and negative, then it will be moving directions. If they will be substantially different, it will mean the cancellation that you just mentioned.
Mm-hmm. So yeah. So those are the models that I'm trying to optimize, and these are plots for all the figures. So x-axis is time step, or how many steps I tried to optimize them, and then y is energy. And so you can see some of them optimize sort of well, some of them are fairly noisy and don't like to optimize. And so I've been having a little bit of trouble with some of these samples.
Can you guide us through the notations?
So the notations correspond to, so SE, SH, those are the same SE and SH from the previous figure, so like band occupation. And then A just means alpha, so alpha electron for spin. And so these top panels are all the same spin state, so it's just alpha electron in the S band of the conduction band and a hole in the P band of the valence band, and then vice versa. You just switch those around and then having a hole and an electron in the P's. And then the bottom row is same occupations, just change in spin. So alpha is the hole states, and then beta electron is the electron state, so you have parallel spins.
Can I approach and show something on the screen?
Mm-hmm.
Would it be based on the ordering in the ascending order? I do not see well the numbers here, too many digits, but would it be correct to say that this energy is smaller than this, and this will be the highest? So that the terminal energy of your optimization increases across the sequence.
It looks that way. It'd be easier to see if I plotted them all on the same chart. But I guess that's one thing to notice, but I looked into some of these models a little bit more in detail, and so this slide just shows the orbitals that I'm going to show for the next figure, so the SE and SH, which seems to be optimizing pretty smoothly. When I looked at some orbitals for some of the later optimizations, I saw that it's hard to see in this figure, but on like the face, there's a ligand on one of the LEDs, and it seemed that the LED pushed the ligand off, or like desorbing from the surface. And so it kind of produced this trap state here on the LED. So this kind of mushroom shape on the surface. Typically there's a ligand on there, which caps that surface state. And another interesting effect it has is that it seemed to, when the ligand's on there, the halides kind of rotate, like on this side. the halides kind of bend or rotate to kind of keep it as a circle, or to keep these bonds connected. But over here, it seems like the halides become disconnected from that lead. Which I'm not really sure what it means, but it's just an interesting observation. That's it must have to do with, since there's excess electron density on the surface, is that the lead's not able to bond as well to halides or other coordinations that it should on the interior.
Can I ask?
Mm-hmm.
I know that the following is likely impossible numerically, but would you think that if this simulation cell is a cube of 2 by 2 by 2 unit cells, it will be replaced by like n by n by n, where n is like 3, 4, 5, 6, this effect will disappear.
The which effect?
Huh?
Which effect?
The symmetry, like what you call trap states and orbital asymmetry. If you take larger quantum dot, the polaron will be localized in the center and will
right,
be
yeah.
absolutely symmetric.
Yeah, for a polaron, it's there should be like a critical size of your dot, because another way to describe polarons is it traps your wave function.
Mm-hmm.
So, say, I guess if your size of your polaron for like in the bulk is like 9 nanometers, and you have a box at 7 nanometers, it's like your wave function will still reach the edges. But if your box was like 15 nanometers, then the electron density would be stuck on the inside. So it would be decoupled from the surface, I guess.
Excellent. So this 9 nanometers is example, or it is exact size of the polaron? It's fine if you do not remember.
It's same order of magnitude.
But it is like close to 10 or close to 1?
Close to 10, I think.
So we never can compute it.
Yeah. I've only seen one experiment paper try to size them.
Okay.
So it's still kind of ambiguous.
Mhm.
And it's going to be different depending on chemical composition too. So it's and I think my next figure, just another, without ligand absorbed, there's also some more electron density on the surface. And that was my last slide, but essentially what I've been doing is I took my starter model, is I just rearranged the ligands in a strategic way that they shouldn't desorb from the surface as easily. And then, so I've done that, I optimized it to where the orbitals look fairly comparable to what they did before, or like my initial good model, and then I just restarted these calculations, hoping that that would provide consistency between all the models.
Done?
Yes.
Let's thank Aaron. And the presentation is open for discussion. I have a question. So, can you please comment, with understanding that it is a strategic plan rather than collection of results, can you share your plans about matching terrains of couplings? Like you are likely generating sets of non-related couplings for each of these configurations, which are arranged in the whatever ascending or descending order. And if you run the dynamics, the system will explore configurations with smaller and smaller energy. Do you plan to use the same set of non-adiabatic couplings for each configuration, or you plan to dynamically change the set of couplings during the dynamics?
The second option.
But
Right.
can you elaborate on this, or tell your vision? Are there any challenges, or it seems straightforward?
Not necessarily straightforward. I guess I put a little bit of thought into it, and I think it's like you would have to put it in a loop so that based on the change of occupations, or where based on your initial condition where you start, and then keep track of populations as the dynamics cool the system or promote population to the band edges, and then as the populations change, you just change the couplings accordingly.
So in directory where you run it, you need to have like set of triple R files for each configuration, and then the code will read them.
And then just do a superposition of all of them essentially.
More questions? Do you have any questions to yourself? That you want
Oh,
to...
I need to get that book.
Oh, okay. Yes, please send me. I'll try if I have it in electronic form. Yeah, thanks for that. Let's thank Aaron once again. And the next presentation is by honorable guest, PhD candidate Braden Witt, who is helping by free will to several of us in very important practical aspect.
Wait, you're staying for PhD, right?
Nope. Eventually. And it's better to make a mistake up rather than down.
Absolutely, yeah.
So there is a popular subject that is being fancy in the community, so-called quantum materials or two-dimensional materials, and all of them are related to different behavior of quantum systems that, as one travels through dispersion volleys and barriers, giving different signatures to magnetism and conductivity. And if we want to go to this direction practically, one needs to screen dispersion, momentum dispersion, not only along high symmetry lines, but do a scan of all like possible values of momenta, and identify specific points where bands touch each other, which are present in some of these materials. So the rest of the story will be presented already.
I think my expertise in this area has been vastly overstated. So I was approached to produce 6 Dirac points from graphene structure, because in reality there are 6 Dirac points in the dispersion relation for the HOMO and LUMO bands. As you can see, it looks like this. This reciprocal lattice is essentially the direct lattice. It's also a hexagon.
For those of us who just woke up or came for the first time, what are those surfaces?
These are energy surfaces of the HOMO and LUMO bands.
As function for what?
Momenta, K points in X and Y space. So there are hypotheses on how these functions look. As you can see.
And I want to give credit to Professor Krzyzewski, who regularly screens literature and pointed our attention to this paper. So
It's only 10 years old, so...
But still, most of us were missing it. And so it is a paper of Nobel Prize holders who were torturing pets. Gaiman Novoselov.
That was never proven.
And in addition, they got the Nobel Prize for graphene, which is one layer of graphite. And in this review paper, they give a simple way how to derive analytically or give reference to whoever did it first, derive analytically the energies of HOMA and LUMA as function of momentum. So X and Y are momentum, and the surfaces are energies of HOMA and LUMA.
Wallace is the name. 1947.
Oh.
This is the guy.
Pleasant to have educated person in the audience. Wallace.
Yeah, thanks to this RMP. Otherwise, I would never know. You were saying something.
That's all I had to say about this slide.
Okay.
Somebody approximated the structure.
Well, stick around for the condensed matter. I'm planning to derive that in solid state.
Okay. Cool. I'll be there.
Commercial ad of course.
So here is what it looks like with something plotted in MATLAB. That function to recreate it. Cool. Looks like 6 points. Okay, my work starts. Or did you have something to add?
Yeah, let me give. Go to the.
Wait, didn't you do it in DFT? I thought you did.
No. Go from this one to the next, but do not talk anything. Do not speak at all. So the previous slide shows analytical expression just stolen from paper and visualized. But if we eventually go from graphene to graphene oxide, or to doped graphene, or to any two-dimensional material like molybdenum disulfide or bismuth selenide, will it be possible to successfully practice the same tight binding approximation, or they may fail for heavy metals? So it would be more reliable to get a procedure of extracting these dispersion curves from electronic structure calculations. And as a guinea pig, we use graphene as the simplest material that shows this interesting so-called Dirac points where HOMA and LUMA touch each other in a conical fashion at several values of momentum. So the question is it possible to reproduce the figure on previous slide? Flip for those of us with short memory. With 6 spikes touching each other via density functional computation.
The answer is yes. It's all over the internet.
The procedure was not straightforward, and Braden was able to do it from scratch just by his by getting some insights. Please share how you did it.
So it was originally suggested to try and use a rectangular box, a rectangular unit cell to produce this. I don't know how the post-processing of these analysis work in the group, but I imagine they're written for rectangular unit cells. Yeah. So I attempted it with rectangular unit cells. Here is just the automatic K-point grid that VASP uses if you choose the automatic mesh option. But I like to see the bigger scale, so I can manually input K-points in either Cartesian or reciprocal space, and so I can see the full distribution.
So what is the black box? Which you at the beginning it tells example file, but example of what?
Oh, sorry, this is the K-points file in VASP. So you need the 4 initial files, right? In-car, post-car, pod-car, and K-points. This is an example of a very simple K-points file where I specify that I want 50 K-points in the X and Y directions and a single K-point in the Z direction. So then it takes that information and automatically computes a grid, a mesh, to calculate K-points on in that space. So, but that kind of gives you only a hard to visualize piece.
So the previous one, Monhorst Pack, allows software to do tricks and use points in momentum space which seems reasonable or symmetric. And sometimes it doesn't match our wishes.
So another thing I also did in the in-car was turn symmetry off. Because it would only produce half of what I'm showing here, which is even worse to understand visually speaking. So if I turn symmetry off, then I can get the full, the full cell that is actually produced with the K-points. So it does double the number of K-points for a rectangular grid, because half of them are identical. But so I can also specify them myself. So this is also an example of a K-points file that you could make. So I just generated this with some simple script where I specified them in Cartesian space, which is fine.
So you replace standard K-points file by things like that you are showing, where first, second, and third are values of momentum of K, and the fourth is.
The fourth is, it has something to do with the number of symmetry contributions of that point. So if you label it as 1, it doesn't sort of calculates it independently of any other possible symmetries that exist. Because I wanted to do everything as manual as possible, I just set it to 1. In this situation, I'm not sure that it would do anything different if you put any other number there, because I turned symmetry off in the in-car still. But I set it to 1 just for my own sanity. And you have to have something there. So.
And the keywords example file can be replaced by anything else.
10,000 is just the total number.
And then you need to tell Cartesian. And then you just write a little script that populates these numbers. Okay.
So here I have just essentially the same thing I have on this slide, just expanded view. So clearly, to me anyway, I do not see hexagonal dispersion pattern of Dirac points. Unless somebody wants to argue that statement.
Can you go back to your unit cell? I mean, this is cute. So so you okay in terms of our beloved solid state physics course, it's a rectangular, two-dimensional cubic lattice with a eight atom bases, right? Is this what it is?
Yes.
Are you sure? I mean, it looks very plausible, but are you sure it replicates like everything, the rest of it, the whole two-dimensional mesh? Yeah.
What's the question?
I'm just trying to convince myself, and I'm sure you guys have thought about it a lot. If this is the correct unit cell, if it's going to replicate the whole two-dimensional mesh, right?
Why not?
Why not? Why yes?
I mean, I can
Because
replicate
standard way to do graphene is you take two atoms and you take hexagonal unit vectors, right? That's
If you just copy paste this box, it will reproduce the honeycomb.
right. Well, it's very unorthodox, if I may say so. I mean, what's the reason that you desire a cubic cell or square cell so much?
When computing observables like currents, transition dipoles, the non-orthogonal unit cells will need corrections in the procedure to compute observables.
Well,
It's not so complicated, but it will need changes.
but I mean, something is wrong there, right?
What is wrong?
You don't see the six.
No. What is wrong with unit cell?
I don't know yet. Don't get defensive.
The
No, it
band
looks
stru-
right to me.
something is wrong with band structure, and therefore Braden is giving this presentation because he found a way to fix it.
Okay. Oh, I thought you was done.
No,
No
we just
way.
started.
You just
We have the whole 2 hours for the meeting,
2 hours.
and you can see the protocol, right?
Right. Nobody needed.
This can go.
So, if I migrate to a hexagonal unit cell and go back to the 2-atom basis that produces the smallest primitive cell, and I compute I use VASP's automatic mesh again, it produces for me this dispersion curve for the HOMO and LUMO orbitals, or bands. Now again, if I want a bigger picture, just for visual purposes, I can specify them myself, and I do in fact see some sort of hexagonal Dirac structure. Not exactly sure if I compare it back to this one, because this automatically chose it and I turned symmetry off, so this should be the reciprocal space, quote unquote, unit cell for this dispersion. But now if I increase the number, I see what I want to see. So I'm not well versed in how VASP reads in K-points, especially, but I have reproduced a hexagonal Dirac point dispersion curve.
The picture, if I may, on the bottom, is this some kind of side view?
Yep, it's a 3-dimensional structure. This is just looking at it from the middle, and then the other one is looking at it as sort of a contour plot.
So you have a little bit of a gap there, right? They don't touch.
True.
They do not.
Well, from the K-points that I calculated, they do not touch. That could mean that my grid isn't dense enough. So I didn't calculate a lot of points, so I don't know. It could be any number of things.
And then, DFT, I mean, who knows what the physical meaning of those quantum energies is? Okay.
The interpretation of your observation can be ambiguous.
Yes.
On one hand, it could be shortcoming of DFT, which may not reproduce expected idealized Dirac code. On another hand, it could be just insufficiently dense grid. So the grid was not chosen to literally hit the value of momentum where the gap is 0.
But you know where this, what is it, KK prime, M and prime, where those points are. Do you know if they're included?
I could check, but I did not. I was just looking for general structure.
This reviews of modern physics, I think they just cited like where exactly this cones are.
Okay. So that
Is this PBE functional?
I'm showing PBE functional, but I also tested other ones. They showed essentially the same structure.
But this figure is the record of success. You got 6 cones as expected.
I did.
So using 2-atom hexagonal cell with this specific K points file does reproduce what is expected to the qualitative level, right?
Yes.
Good. So do you have a vision why rectangular cell didn't help? Or you already commented on that?
I don't have a direct solution to why, but
But any thoughts, like any restrictions to use of rectangular cells? You just observe that hexagonal cell works better in this specific case. Okay,
essentially that is my thought process so far.
but if, okay, And can you comment on the range of values of k vector? Why one cannot use the values of k absolute value bigger than 0.5?
Well, essentially I did.
Okay, so just give more comments, educate us.
Well, I don't know how VASP does things. That's why I just sort of took a stab in the dark and kind of tried to go outside. Because I wanted a bigger picture than this. I wanted to see, if I could, I wanted to see multiple replicas of this calculated by VASP by including more points outside of this quote-unquote unit cell in the reciprocal space for the dispersion. So I kind of forced it to calculate outside of that cell by making it calculate bigger k's than 0.5.
So which keyword in which file does reflect your
The k points file.
okay.
By specifying these Cartesian points, I specified k points that were outside of the 0.5 threshold.
But the values that you're showing in this box are all smaller than 0.5.
But reciprocal values go like 1 over that value.
Okay.
So
And let's go to the next slide. So I hope you give permission to follow what you did with appropriate credit to you. So can you just comment on if anyone of us will follow your procedure and take over the samples of the files and continue? Are there any instructions?
I think mainly just in the yellow text is the most important part. So the directory structure is more or less obvious to me, at least. The 2 atom is the hexagonal lattice, and the 8 atom is the rectangular lattice, or unit cell. Excuse me. And then, of course, I specified the functional, and then the manual is the one that I've been showing versus the automatic. Automatic is the VASP generated mesh, and the manual is the one where I specified it.
So automatic was not working and manual did work.
Well, automatic probably does work, but it does not show
6 points.
6 points explicitly.
In this specific example that you studied, the manual works for sure with guarantee, and automatic may or may not work. You wash your hands.
This is what it seems. Yes, and it especially does not characterize the points around all 6 Dirac points. Because here it shows explicitly 2 where they almost touch, right? But there should be 4 more. And so by manually choosing the k points, I can visualize all 6. One may need to fiddle with which k points, but the automatic doesn't seem to show quite as much as you can get. And so, manual and automatic ones are the ones of importance, and inside there's a Python file that just extracts all the points you need to plot and puts them into the .dat file, homolumo dispersion.dat.
So how many total k points in your most successful?
10,000.
10,000 k points.
That's too much.
Okay. So, David already left. But the idea is for those of us who compute non-adiabatic couplings is with momentum dispersion to have this instead of 4 k points use like 10,000. Ideally, maybe it will be not practically possible, but if we do need this high symmetry points, it will be really huge number of momentum. Maybe it will need some additional numerical sources, and we need to write a special proposal for it, but right now it looks like in order to get this points, one needs whatever Braden advises.
And if your structures that are interesting are looking like these, it's really easy to interpolate data between the points. So you wouldn't need 10,000 for this system. You could just fill in the gaps pretty easily.
Did you try? Because I think in VASP you can tell it to sample like the high symmetry points.
Yeah, I did that too. There's a directory called line search there.
That didn't really help either.
Well, I mean, it gives you stuff, but I was instructed for a fully expansive search, which is what I did.
Okay. And before we go for a round of applause, can you scroll forward one more and hit the movie to play?
Can I hit the center button or?
No, this mouse. So the goal is to reproduce the same thing with 10,000 K points instead of 4, which are shown here. Okay, let's thank Braden. And the presentation is open for additional discussion.
Quantum Espresso has they have the input coordinates and K-point mesh on their frequently asked questions. They probably got so tired of everybody asking how to do graphene, they show an example. I mean, I know it's a different animal, different software, but they claim that their software does it right. So if you want to go all the way, it would be interesting to see, if they would see those gaps or the cones will be touched. Just a comment.
More suggestions?
Was the model strained at all? Or is there a little strain?
I looked at the forces and they were fairly small enough to where it shouldn't matter.
So I think, well, I guess I don't know how much asymmetry, but like even a little asymmetry should open those gaps a little bit.
And that could be.
You're right, but even without any strain, it's already a big challenge. Even with if you do tricks that Braden is suggesting, like making less K points and interpolating between them, it is at the limit of computational abilities. We typically do like 50 orbitals with single K point, like 50 electrons, 50 holes, so total 100.
Mm-hmm.
And here we have only HOMO and LUMO, but 10,000 replicas of HOMO and 10,000 of LUMO, which is likely not possible when you hit some limits, even if you do not move any atoms.
I was just wondering in his models that he did, if there was a little bit. Like, I wasn't suggesting to add strain.
Also interesting. But yeah, I don't think they were large. So.
If you make cell bigger, your Brilliant zone is becoming smaller.
It's a perfect question, but I do not know the answer. If you
I
can answer the question yourself,
can I finish?
please, but we need to have a brainstorming session on this. Please finish.
Okay, it's probably not the case, but when you don't see the 6 cones, is there any way that simply because you didn't zoom in enough that maybe they're buried somewhere like very close to the center? No? Where is it? No, probably no way. In principle, you should see the same electronic state. So I like square cells too myself.
but I don't know, if it's there, it's not obvious. But I mean, it isn't the highest grid point density, but I feel like it would be, because we do see 2 Dirac cones for some reason.
Can it be that when it's more bands, like when changing the size of the simulation cell, the like half of a band starts rolling over, and now it is maybe Luma plus 1.
But no matter how you count it, I mean, the physics should be the same.
Well, here physics, yes, and all observers should be the same, but here we explicitly draw only Homo and Luma. That may be to represent the same energy range for all observers. One needs to plot not only like Homo and Luma, but Homo minus 1, Luma plus 1 for all larger simulation cells.
So they would be degenerate with this, right?
At certain points, not
Right.
not everywhere.
Did you do it?
I could look.
This is interesting because having larger number of bands with smaller number of K points is so much easier to process in follow-up procedure. Because this 10,000 is
It's a non
it's not possible.
not
It's
feasible.
maybe once in a life. Is,
Forget about it.
so if you can reduce it maybe to a couple of hundreds K points, still will do it.
Again, I keep bringing up Quantum Express. I haven't tried it. I just look. They just cite some high symmetry points and claim that this is sufficient to simulate graphene. Definitely not 10,000, maybe 10. I don't know. Did I send you the link? Or I never did. Shoot. I was just looking at the sent mail and realized I didn't.
But these high symmetry points would be reasonable for materials that we have experience with. And if you start with some very new unknown material, it may need the screening of the overall area of definition for momentum. Like if you want universal procedure that will select materials with or without Dirac points or something like that. More questions or comments?
My God, is that me?
Other Ivan, do you have any comments or questions? But there is something we can borrow from Brain.
Yeah, I guess I can try the keyboard stuff.
Fatima, do you have any questions to Brain? No? It seems straightforward procedure that one can repeat. Okay.
I have
is
a
there-
question. So this box is the unit cell? So
No, it is a simulation cell which is bigger than unit cell.
Oh, sorry.
And it is what
It's
Professor
simulation
Krzyzewski
cell.
was.
So why these atoms outside of this box?
It's outside the box, it's more of a visual representation, right?
Why didn't you put atom at the corner?
Which corner?
It annoys me. No, it doesn't matter. Corner 0, 0.
Oh, why one doesn't match origin and first atom?
Yes, the
Which atom was your favorite?
equivalent points, if possible, should be associated with actual atoms.
Brendan, can you show the next slide for Fatima to show the unit cell itself?
I understand the difference between unit cell and simulation.
Yeah, but so here is very specific unit cell, which includes only 2 atoms, and the angle between axes is not 90 degrees. So it was a trick from our point of view, maybe standard thing.
60.
From 60
No,
and 30.
hold up.
No, 120. and
120. Oh, this is horrible. I need to sit down.
120 plus 60 will be 180.
Actually, well, it can be figured out. My student used to say.
Okay. And Braden got what is expected from theory and from experiment only with this non-rectangular unit cell. In some sense, although the number of points is really huge, but it is very small cell. It's just 2 atoms, and each single K points goes maybe within like seconds, right?
All of his calculations were quite trivial, time-wise.
Okay, so calculations are possible. Maybe processing non-adiabatic couplings and collecting intermediate data will be challenging.
But if you wanted to dope one of these, though, if you wanted to dope them, eventually,
Then forget it.
yeah.
Because then one cannot use the small unit cell, and we need to do what we just discussed. Have larger simulation cell, and then making this roll over of bands, or just have a little more brainstorming to understand how to represent this momentum distribution for larger simulation cell, where this Dirac points will come into play.
It's a crazy idea.
Please,
I mean, this is something we have
we
been
came
doing
here
all-
for crazy ideas.
I mean, this is not very expensive. Can you take, I don't know, whatever, 10 or 20 or 50 of these 8 atom unit cells, right? That definitely should be a genuine chunk of graphene, capturing all the properties. I mean, you should see the same picture. So you should see six states that touching 0. So on and so forth.
Well, I remember we tried to do that with our Twisted, right?
Right.
But even at 100 atoms, it was pretty expensive to do some K-points.
Twisted is the next step over our heads. Let's just reproduce something reasonable for a single graphene.
But as you add atoms, it gets really expensive, and so you would never be able.
No wait, but but then you only need to do a gamma point, right? Because
If you use huge number,
Yes.
and if you screen intermediate transition between them, then we can use a little bigger cell, little smaller number of K points. Bigger,
true, yes.
so it will be like conservation. Number of K
Right,
points
yeah,
times
yeah,
number of atoms equals constant if you want to keep precision. So we can declare this conservation law and name it after you and Braden.
What conversation? Oh,
Conservation.
conservation.
Yeah.
Okay, Braden, you can take it.
How much vacuum do you apply for the z-axis?
I tried multiple values of it just to check to see if that was also the problem, but I went up to 15 angstroms, and it looks the same as if I do 7. So
Very cool. Yeah. Last chance for questions. If not, let's thank Braden once again. So many thanks to everyone for presenting, attending, and contributing to brainstorming. Meeting is complete and dismissed. Next meeting Tuesday, 4 as on this schedule. Any changes will be announced, and there will be another sequence of group meetings from Professor Kivener group on Friday. And I don't know if it is publicly available, but there is another sequence of meetings by Professor Krajewski group on Tuesdays. Everybody?
What? No.
No? No? You don't do it yet?
Well, we read Griffiths and such.
Okay. But if you need bigger attendance, you can announce it more.
No.
Okay.
I'm already pretty uncomfortable in my office with 3 people.
If anyone was taking notes, not for him or herself, it's possible to share and use authors as a feedback. It's not mandatory, it's only the option. And I'll stay here, and everyone is welcome to stay here and chat more, but formal part of the meeting is done, and I'll stop the recording. So
Okay.
after that,
I second the notion.
you can criticize